Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
We're putting the name of the project as Project 3. Next, the unit system we're considering SI unit, and all others as usual. Pressure will be Pascal and velocity meter per second. Next, it is an external analysis. The gases we'll consider as air particles. Next, default wall thermal conditions and roughness we don't know, so we can skip this part. Next, finally we have to find the velocity of air in x direction. Let's velocity of air in the x direction will be 30 meter per seconds. Now see one thing, like the bike or the motorcycle will be moving in the negative direction of x-axis. That means velocity of the bike will be negative and the velocity of air will be positive, 30 meter per second. Okay, finish. Now it is ready for analysis. Before that we have to apply some boundary conditions, the speed of the wheel and the base part also to be provided. First of all, we'll see the computational domain. Edit definition of computational domain. The domain is the actually total space for this calculation or this analysis part. If we make the domain small, analysis can be done with a very short time. We're making the domain little bit smaller, in which the time for analysis takes very less time. Okay, this part we can reduce little bit. This is the domain, right? Top part also can be reduced little bit. Okay, this is the domain. Okay, done. This is our computational domain. Now we can hide this part and go for boundary conditions, right? So starting in boundary conditions, insert boundary conditions. Now in this case we have to provide the velocity of the tires or the wheels. By the same time, as the wheel is moving in the negative of x direction, so we have to assume that the base is also moving. With respect to the wheel, the base is also moving. The relative velocity of these two will be, actually one will be positive, one will be negative. Suppose the wheel is rotating with a speed of 40 meter per second, then the base will be moving with opposite velocity. The direction is opposite, right? So in this case, first of all we are considering velocity of the base. It will come from these wall conditions. We are considering real wall conditions, and we can consider that wall motion is equal to 40 meter per second. This base is moving with a speed of 40 meter per second. Positive direction of x-axis. The velocity of the base is equal to 40 meter per second. Therefore, the velocity of the wheel will be minus 40 meter per second. Okay, this is done. We're considering linear velocity. Okay, but to select the base, of course, yes, base velocity is plus 40 because it is moving the positive direction of x-axis. You can say angular velocity we are not providing, we are providing translational velocity, or linear velocity is equal to 40 meter per second. Okay, next one we have to provide velocity of the wheel. So again, boundary conditions, insert boundary condition, walls, wall motion. We are considering real wall, and let's consider the velocity of the wheel as minus 40 meter per second. As it is moving in the negative direction of x-axis, it will be minus 40. We are considering linear velocity. We can provide angular also we are taking minus 40 meter per second. This one done. Again for the other wheel also we have to provide velocity. So again boundary conditions, insert boundary conditions, walls, wall motion, and the linear velocity will be minus 40 meter per second. So to select that wheel, let's make this one a little bit bigger, then selection will be better. Done. You can check. So all the boundary conditions have been applied properly. Now is to select some goals. Insert global goals. We have to see pressure, velocity, the normal force, shear force, etc. Right? First of all, see total average pressure, average velocity. At the same time, you want to see normal force in the x direction. There is a drag force. Our aim should be to reduce this drag force. Shear force in the x direction. We want to see frictional force and also what you see average shear stress. These are our goals. Again, we want to see some surface goals also. So insert surface goals. We want to see average total pressure, normal force in x direction, average shear stress, and we have to select that specific surfaces, right? We'll select the surface one by one. It will take some time. So we have selected all the surface and provided surface goals. Surface goals of normal force in the x direction. You can find frictional force, average shear stress, and also average total pressure. All the goals have been defined properly. Next we can run it. Solver is finished, so we can check the results right now. First we will see results from cut plots. Insert cut plots. Along this front plane we can see the different values of pressure, temperature, etc. velocity. First of all we see pressure in the form of contours. Let's see. So initially, before striking with the front plane of the bicycle, the pressure is little bit higher, then it is reduced. We can see velocity also. Velocity in the x direction. Yes, like velocity before striking, it is little higher in the range of more than 18 meter per second. It is in the range of 18 to 30 meter per second. Velocity, that is velocity of air. But after striking, some region is there where the velocity is coming down little bit. Right? You can see other parameters also like temperature, pressure, etc. anything. We can see like temperature also, it will not change that much of temperature. temperature will be almost same throughout this one, about 20 degrees centigrade normal temperature. Now we want to do one thing, like you can see this one in the form of an animation. You can see the pressure. We want to see pressure in the form of an animation, right? So cut plus 1, play. This is in the form of contours. You can see again in the form of like vectors also. Cut plots, clear and hide. Cut plot 1, edit definition. What you see in the form of vectors and isolines. Let's see this one. See the vectors, and this one is isolines, right? We can simulate this one. Let's see the simulation. Play. Even we can see in the form of like mesh also. Cut plot 1, clear and hide. Cut plot 1, edit definition. What you see in the form of mesh. What you see mesh and contours also. Mesh and contours. What you see? Let's see that one. That mesh we can refine as per our requirement. We can mesh better way. Okay, so clear and hide this part. Next one, we want to see surface plots. Insert surface plots. We want to see pressure and velocity, etc. both. First we'll see pressure. So we can see all faces, right? So we want to see surface plot across all faces. Green check. It will show pressure, velocity, etc. across all surfaces. First of all, we can see the pressure here. It is pressure is almost similar, no change at all. It is in the range of like, it is in the yellowish green range. That is here it says little bit of more compared to atmospheric pressure. You see the velocity right now, velocity in the x direction. Velocity is in the range of 3.5 to 18 meter per second, and at the tires a little bit less. You can see shear stress also. Shear stress is less than 2 megapascal throughout. Let's see velocity, normal velocity. It is almost constant throughout this body velocity. Next one, want to see some other thing, like we want to go for flow trajectories. This part we clear and hide. Next one we'll go for flow trajectories. That means how the air particles will be moving. Insert air trajectories. Numbers of bubbles to be 200, and we want to see in the form of lines and arrows. Let's the visibility a little bit more. Now across some plane we want to see these things. Let's see the plane as a right plane. Green check. Still it is going on. It will take some time based on PC capabilities. That is done. Now you can see in the form of an animation, right? So we'll see this one in the form of an animation. First of all, we'll clear and hide this part. Flow trajectories, play. can see from back side also. You can see air particles are moving very smoothly, and it is having very less resistance from this bicycle. We can do one thing, like we can see the results in a different way. Like if we make this domain little bit less, we can view this profile in a better way, but it is not required. Now I want to do one thing. We can see goal plots. So show trajectories, clear and hide. Now we want to see the results. We want to see our goal plots. Insert goal plots. We want to see all the results. Show. These are the summary of the results. You can see in the form of plots also. First of all, you see average pressure was almost similar to atmospheric pressure. It is not having any kind of change. And also you can see the average velocity is 29.343 meter per second. With these results we can go for detailed analysis, and finally you can see all these results in the form of some plot. Here it is. The total pressure is coming down to near about atmospheric pressure. It was very high at the beginning. Velocity also, all these things we can see. Let's make the graph a little bit. Average velocity, normal force, frictional force, shear stress, all these things we can see here itself, right? And we can go for detailed analysis with this data, right? So this is all about today's aerodynamic analysis of a bicycle using SolidWorks. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.